All right, in this question, we're looking at a uniform electric field is produced between two parallel metal plates. The electric field strength is 1.4 by 10 to the 4 newtons per coulomb. The potential difference between the plates is 350 volts. Calculate the separation of the plates. So you may recall that electric field E is equal to, newtons per coulomb suggests force per charge. But remember, that's equivalent to voltage per distance. And so here, because we're calculating the separation distance, we want to kind of use this form of the equation to solve. So if E equals V over D, then these two can switch spots, right? Multiply both sides by D, divide both sides by E, and you've got D equal to V over E. The voltage they gave, 350 volts. The electric field they gave, 1.4 by 10 to the 4. And instead of newtons per coulomb, I'm going to write it as volts per meter. So there, my volts will cancel. I'm in meters. Good. Remember, a volt per meter is a newton per coulomb. You can sort of check the base units on that before, right? And so the calculation just becomes 350 divided by 1.4 by 10 to the 4. Let's use the on-screen calculator to see it. 350 divided by 1.4 by 10 to the 4th. There's my 14,000 I'm dividing by, so I get 0.025 meters. And you could maybe round up 0.03, but I'd rather leave it like 0.025. I think that's a better answer. All right, so you should have got that for 2 marks. If you did, awesome. If you didn't, make a correction and give yourself partial credit. Item B here says, a nucleus of mass 8.3 by 10 to the negative 27 kilograms is now placed in the electric field. The electric force acting on the nucleus is 6.7 by 10 to the negative 15 newtons. Calculate the charge on the nucleus in terms of E, where E is elementary charge. Okay. So I think we've already got the electric field, E, and we know that it's force per charge, and now we're trying to solve for the charge. So we sort of use the same strategy we used last time, make Q the subject here, and so it's going to be the force divided by the electric field strength. They tell us the force, the electric force acting on it is 6.7 by 10 to the negative 15 newtons, and the electric field was 1.4 by 10 to the 4 newtons per coulomb. So this will give us coulombs of charge. And so we won't be done, right? Because it wants it in terms of E. So let's just, sort of calculate this as an intermediate step. I'll let you guys do this on your own calculator. I don't need the on-screen calculator for all of them, right? 6.7 by 10 to the minus 15 divided by 1.4 by 10 to the 4. What did you get, YouTube? 4.8 by 10 to the negative 19? Well done. Now that's coulombs of charge. And so now we got to recall that you could go back to the sheet of data that I said might be helpful in solving this. Say, well, what is an elementary charge? And so on that list of data, you will find there's 1.6 by 10 to the negative 19 coulombs per electron, per proton, per elementary charge, right? So it's the charge on either a proton or an electron, just positive or negative. So I got this value still in my calculator, and it's actually 4.785. I've rounded it to 4.8. So we'll just see if I divide that number in my calculator by 1.6 by 10 to the negative 19, I get a number that's so close to 3, might as well be 3. So my calculator tells me 2.99. Now, if you probably did this calculation, it would be exactly 3. But again, I left the sort of more precise value in my calculator. And again, you get a number it should be a whole number, right? Like we can't have partial, electrons. And so it's integer multiples of elementary charge. So you should get a whole number very close to it so that you can round it and feel good about, okay, that's the whole number there. Now it says calculate the mass in U of the nucleus. In U. So I think this is just a conversion because they've given us the mass of the nucleus, right, in kilograms, and we just have to sort of, again, rely on our sort of data that's sort of given. So they tell us, if you sort of went back, that's why I included the data in the formula for the quiz. This is the full paper, but on the quiz that I uploaded, we have both sort of this page and the other one. And so here you can look at 1U, a unified atomic mass unit, 1.66 by 10 to the negative 27 kilograms. And so that's the number we need right there. That's what you should have sort of extracted out of that. And right up there, you see there's elementary charge, 1.6 by 10 to the negative 19. So it's helpful. So 1.66 by 10 to the minus 27 kilograms. That's a unified atomic mass unit. So if they tell us that the mass is 8.3 by 10 to the negative 27 kilograms, and we know that there are 1.66 by 10 to the negative 27 kilograms in one unified atomic mass unit, then we just sort of do that division there. So 8.3 by 10 to the negative 27 divided by 1.66 by 10 to the negative 27, that equals 5. Remember, this was 3. Now it says, use your answers in B1 and B2 to determine the number of neutrons in the nucleus. Okay, so the charge in the nucleus was 3, but it's got a mass of 5, right? And so it's a unified atomic mass unit because it's sort of either the mass of a proton or a neutron. They're so close that we can just kind of unify them together, and it's about this. So if there's 3 charges, right, 3 elementary charges, remember that's the charge on either a proton or an electron. We're talking about the nucleus now. And so those are our 3 protons, which means that this thing has a mass of 5. There's got to be 2 neutrons. So it's just the difference between these, right? So in other words, we know there's 5 nucleons, and because the charge is 3e, we know 3 of these 5 nucleons must be protons, and so the other 2 are the neutrons. That one's not too bad there.